Welcome back to the hyperbolic coding chamber. This is day 35, LeetCode every day. Reflections on yesterday. I said I was going to do like one problem. Ended up doing 3 problems. It is what it is. Do more when you can. So that was pretty cool. Got to dunk on I think we did dunk on some problems. I actually don't remember. I think we did 3 some. No, we did longest substitution without repeating characters, so that was good, I think. And when we did 3 some, we actually couldn't come up with a good enough solution. But I do kind of remember some intuitions behind that. So we have BLOT as a problem, blot, and clone graph as well for today. So I'm hoping that maybe we can do something about that. That being said, general reflections on the grind. Not feeling that great today. I actually feel kind of sick. Thinking I got maybe some kind of nasal drip issue that is leaking mucus down my uvula into my digestion chamber. That being said, feeling a little bit sluggish, a little bit slow. Also, my brain is a bit fried. So yes, I'm thinking that we still have to do the work anyway. It is what it is, but I'm thinking that tonight I'm going to try to get to bed a bit earlier, but still try and get the same amount of grind in. But it is what it is. That being said, excited to do some of these problems today. I feel like binary tree level order traversal we have a good chance of doing, as well as clone graph, but we'll have to see about that. Generally, the plan is to keep doing problems, and hopefully if we go slow enough, we can go really fast. I think I definitely have been slacking a bit on revision, but the new problems have been coming in well. I think there's a nice contrast between old problems and new problems, which helps, I think, facilitate learning. But it's hard to balance it because you do new problems and old problems. Have to find a solid balance that you feel like, you're making good progress all around. But like we always say with the leaky bucket example, if you want to be able to fill a bucket of water the fastest, the best solution isn't to get a bigger hose. It's probably to plug the leak at the bottom of the bucket. So that's why we have revision, but I probably should be doing more revision. But that being said, make sure to join the Hyperbolic Coding Chamber Discord. At the same time, if you feel like you're doing something similar, interested in doing something similar, if you're already doing this, then feel free to drop a comment, drop a like, drop an insult. So that is pretty cool. So yeah, I'm gonna sign up for the 1 hour and 30-minute session. Now I'm thinking, I'm kind of dreading the fact that it's gonna be 1 hour and 30. So I'm just gonna make it 1 hour and 35. Just to kind of get in the habit of pushing. It's not a lot, but hopefully over time it'll make a difference. I think the Atomic Habits books mentioned that, like, over time, right, if you were to make a 1% increase on something every single day, at the end of the year, the manifold gains on that minor increase ends up being particularly useful. So I'm hoping maybe getting into the habit of pushing myself a little further when I think I don't feel like I can. It's probably a good habit to get into. That being said, 1 hour and 35. And then we're going to start with binary tree level order, go to 3 some, and then go to clone graph. Actually, maybe we should do 3 some first. So that is what we'll do. Make sure to join the Discord. Thank you to anyone who leaves a comment. Thank you to anyone who pops in. Yeah, so I'm just going to jump into it. 1 hour and 35. Let us begin. So we have function 3 sum. We have an array of numbers. My throat's also a little bit weak. Given an integer array nums, return all triplets num sub I, num sub j, num sub k, such that I does not equal j, I does not equal k, and j does not equal k. So they're talking specifically about indices here. And num sub I plus num sub j plus num sub k equals 0. Now there's a potentially naive solution here where you can do this in n cubed, where you could iterate for 3 times through the array and just check all possible combinations. However, that would not necessarily be feasible given a large enough input, right? Because that would be n cubed. And we know that the length of the array can be up to 3,000. So that I think should be 3,000 times 3,000 times 3,000, which is a lot of work. Additionally, to do this in n cubed time, we'd also need to be able to dedupe them, right? And so notice that the solution set must not contain duplicate triplets. So we have -1, 0, 1, 2, -1, 4. We have 3 triplets which represent numbers being added up to the target number, which is 0. So that being the case, you also have to load all those 3,000 times 3,000 times 3,000 times 3 factorial potentially different keys into the set. That being the case, it's not going to scale, and we know it's not because we actually tried to implement it before. And so the solution is saying that out of all these indices, if we consider groups of 3, this adds up to 0, this adds up to 0, and they're also been deduped. So there's no duplicate triplets here. Not in the sense of indices, but in the sense of actual values. So we can see that 1 plus 0 plus -1 equals 0, 0 plus 1 plus -1, which is technically the same, right? And the output is only these 2 bottom triplets, right? So there's a few different versions of ways to solve 2-sum, but I think there's another version in which the solution can be done in log n time, right? Considering the array is sorted, right? We can simply edge these 2 pointers, right, towards each other, or away, well, only towards each other, right? So if we want to add a sum up to, let's just say 9, right, the array will be sorted. If our current sum is too big, right, then we'll decrease our largest number to the next possible index, right? And so if our number is too small, then we want to add just a little bit, right, not too much. So we would increment our left set pointer, right, to try and sum them up to a value that makes sense. That being said, maybe we can augment this to work for 3-sum. So we see 0, 1, 1. There's no triplet that can be added up to some 0. So we return a 0, return an empty array. We see that 0, 0, 0 does sum up to equal 0. So this is the only possible triplet that sums up to 0. So let's imagine this, right? The 2-sum version of this, right, requires a sorted array, right? And we're going to be iterating towards the center for both. So we need to calculate 2-sum given 2 indices, right? But we're actually supposed to solve 3-sum. So maybe what we can do is iterate through the entire array. Well, maybe if we have to sort it first, right? So we'd sort it first, right? And we'd iterate through the entire array, right? And then we could calculate 2-sum given 2 indices, right? And so I think if we do it this way, then we end up, I think, only having unique versions. So let's try and figure that out, right? So if we have this as our array, right? And now we want to sort it. So we have 0, no, we'd have -1, -1, 0, 1, 2, and we actually messed up because -4 should be here. So let's say our start pointer is at -4. Maybe our left pointer is at -1 and 2, right? Does that sum up to our target, which is 0? No, right? So how can we do better, right? And so what we could do is, since our number is less than it, right? What we could do is move our left pointer over to -1. Well, this now equals 0? No. If we move it forward again, does this now equal 0? No. And if we do this one, we get the closest we possibly can, which is -1 if we sum them all together, but doesn't equal 0. Now we'd go to -1 and we'd say, all right, -1, and then we're going to add -1, -1, and 2. Does it equal 0? It does, so we can add this as a triplet, right? We'll increment. So we add that as a triplet, right? And then we would go forward again. We guess we'd say -1 plus 0 plus 2 equals 0. No, so we know that we want to keep going even if we find keep going even if we find success triplet. Right, then we move to this -1, so we'd have -1, right, with our starting pointer, then we'd have 0, then we'd have 2. Does this equal 0? It does not, so we'd increment it. What if we add -1, 1, and 2? Does not equal 0. So now we're going to go to 0. We have two left and right pointers. If we add all these together, does it equal 0? No. And if we increment right, it'll be smaller. So the common way when you iterate over two things are iterating towards the center is to stop when they pass each other. So in this case, this indice for our right pointer would pass the left pointer and we'd stop. Then we'd go to -1. Right, and I think once we get to the end, we should have worked with all possible combination. We should have generated not too many of them, but still we could utilize a deduping process, and this deduping process can take a while, but it should be faster than our original version, which had to do n-cubed iterations. So let's try and implement that. And what the bottom will have is a dedupe process. And so if we have, let's say, an array of triplets, like all the ones we would have, right, how could we dedupe them? Well, we could sort them all, and if we sort them all, will be n log n bound, right? And then we'll just double check to make sure that there's only one of each of these groups in the. So we could iterate, we could sort all of the triplets, and then if we sort them, we could insert them into a set. And if we insert them into a set, then we should be good to know which ones are duplicates, which ones are not. So this will involve a set. So we don't have much time left. Let's try and implement that. So we're going to sort it first. Right, so we're going to have nums dot sort a comma b, right? And while a is less than b, so we're going to sort it in ascending order. We're going to iterate for const. We'll just do it like this. We'll let I equal our start. I is less than nums.length I plus plus. And then we're going to, here we want to do a calculate to sum given to indices, right? So this version just requires 2 pointers, right, left, which is going to start exactly at I, and right, which is going to start at nums.length minus 1, the last element in the array. While left is less than right, we want to say, hey, if nums sub I, right, which is where we're currently at, right, and we actually don't want to start at I, we want to start at I plus 1, right, num sub I, right, plus num sub left plus num sub right equals 0, and that's awesome. What we have here is for our triplets array, we can now push nums sub I, right, nums sub left, nums sub right as an array. So we're gonna have an array of arrays. So then we're gonna have those values, right? I want to say, right, we can actually just do sum because we're going to be using this a lot. So we'll say if sum equals 0, then we have a triplet, right? Else if sum is greater than 0, right, then we want to slide our right corner down. Say right minus equal 1. Else if sum is less than 0, we're going to want to increment our left pointer, right? We're going to keep doing this until we're done, basically, and we'll have acquired a couple of triplets. So we'll keep going even if we find one, we just push it on, right? We don't actually stop. So after this, right, our for loop should end, and now we have to dedo, right? But let's just print this out to make sure that our assumptions are correct, and we'll just return an empty array. So we've said num, it's supposed to return nums. I named this variable triplets, but what we're actually pushing on to is triples, and that's just a keyboard error. So we have a terminate called after an instance of bad alloc. Oh, wait, so what we're given is an array of numbers and we're asking to be sorted. Saying I is less than 0, left equals I plus 1, right equals. So that's an interesting error. For loop makes sense. Sort, I think, makes sense. Maybe our return is not allowed. Let's check our brackets. I've never received this error before. I equals 0, I is less than nums.length. So let's just start commenting out code and see where our issue is. So triplets is an array, and what we want to push onto it is an array of elements. We're saying num sub I, nums sub left, nums sub right. Okay, so maybe something is actually going on in this while loop. So we're getting a bad instance of alloc, saying while left, which is I plus 1, I is equal to 0, left is less than right, which makes sense. Num sub I, which is an element within nums, num sub left, which is an index, num sub right, which is also an index. Maybe it's this triplets.push line. So that makes sense. So now our time limit is exceeded. So if our sum equals 0, so if it does, then what do we want to do? We want to keep looking, right? So if we did left plus equal 1, like we said earlier, maybe that could make sense. But actually, maybe we will just stop then. So if we find a new combination, right, we sorted it, or we find a new combination. We find a new combination if we're having our sum equals 0, then it seems like this is constantly happening over and over and over again, which is why I think we're getting bad alloc. But when we do it like this, we realize that we never end. So if we go back to our original premise, sort the array, we have -4, -1, -1, 0, 1, and 2. Right? When we find one that actually equals 0, right, which could be not possible with 4, when you get to -1, right, maybe that's possible with -1, -1, and 2, right? Very possible. Maybe you want to stop there. If we want to stop there, we can still increment to the next value, but then we wouldn't get 1 either. So you wouldn't get 1, 1. 0. Maybe we would, right? When we get to -1, we'd have 0 and 1. So let's assume that maybe we do get there. We'll still do triplets.push, but we'll just say to stop the loop, left equals right. Right, or you can also do break. So we'll just do break. So we are getting the numbers that we're actually interested in, but I still think we need a deduplication process. But honestly, let's actually test this. So you still need a deduplication process for all the ones, so we can do that with a set, and what we will do is for triplets for each group, we're going to do group dot sort a, b, a minus b. So we're going to sort it all in ascending order, right? Then we can do triples dot for each again, and for the group, we'll just load it into the set. So say set dot add say group sub 0 group sub 1, and I think there's definitely a better way to do this in JavaScript. We could use map and additionally reduce. Right, we'll add it to the set, right, and then we'll say to deduped, right, is going to be an array, and this array is actually going to be created from the keys of set what we're going to do is do dedupe.push, right, and then we'll spread the string, right, which is going to be 3 letters, right, into an array, and then we'll do spread it into an array, and we want to map through them, right, and we'll do parse init car, and then we can push that array on so we can return deduped. We keep saying triples, we mean is triplets. So we spread the key, which is a string, getting non, so it must be something we're misunderstanding about set.keys. So let's take a closer look at that. So just print the key. So it's -1, -1, 2, negative 101. And I see, okay, now I see why. So a better way to do this instead of recreating the set would just be to iterate over the const group of triplets, and I think one way to fix it, we could just cast it how we're doing here, except we could just check, so we can say, hey, the key is going to be equal to this, and so we can just say, hey, if set doesn't, if the set doesn't have the key for this group, then dedupe dot push group. Some things is amiss, so let's check what's actually in the set. Then we'll check what's actually the keys that we're looking up. So the set does have -1, -12, -101, and then the key is indeed -1, -12. And set, does it have this key? Oh, so I see what we're saying. So we need, this is the set that proves the one we have already. So maybe we could create another set for dedupe set, which is a little bit tough and would be difficult to maintain, but just for the sake of the idea, we could say if dedupe, dedupe set, So I think what we're seeing is that we actually don't have to pre-populate the set. We can go one at a time. That way we don't need two sets. So what if we just say, if the set doesn't have the value, then set.add key. That way I think it's clearer what's actually happening. So let's try this long term. So here we're getting an incorrect answer. We should have gotten a -211, but we're not, And so I think the root of that is that we're stopping here. So So the dilemma I'm having is, if we do find a triplet, we want to push it on. But if the sum equals 0, we never actually do left or right anything, So if the sum equals 0, which means we found something that does equal 0, should we increment left? Should we increment right? It's unclear because in both scenarios we have a chance to miss. Or actually, maybe we don't. No, I think we do. In both scenarios we have a chance to miss a potential. Both scenarios we have a chance to miss a potential triplet. So how could we go about doing this? Maybe we could do, we don't want to stop because we want to generate all possible versions. But the mechanism by which to do that is unknown. So maybe we could do so if our pointer starts at -2, we'd go, our left pointer would be 0 and our right pointer would be 2. And then we do so on and so forth. One that does sum up to 0 is our initial starting point, which is -2, 0, and 2. So if we know that to be the case, if we know that it sums up to 0, what do we want to do there? Well, we could increment 1. right? And maybe that's okay. You could always increment left, right? So we'd keep making progress in the end. Does this equal 0? It doesn't, right? And the reason why is because it's too large. So we move 1 down, we'd have -2, 1, 1. So maybe incrementing left does work because in the end we're iterating from left to right. So let's do left plus equal 1. So we should be able to end here. So for a case of all zeros, we have an interesting problem. So I think we can do this probably all in, maybe we could do this all in one pass. So if our sum equals 0, right, maybe we could have the set all the way up here, because what I'm thinking is that we end up pushing on pretty much every permutation of 0, right? So we could cut that part out of the equation out, right, if we just made sure that we never push anything onto the array that we'd already seen before. So in this sense, we wouldn't necessarily need deduped, since triplets would be more guaranteed now. So maybe we could do const r equals this new value, and we could even name this group, right? And then instead of saying triplets dot for each, right, we'll just say, hey, sort this group. And then if we sort this group, then what we would like to do is check, right, we'll create a key for it, and we'll pretty much do everything we did at the bottom. The key would be created, right? If the set doesn't have the key, then we push it on to triplets, right? Then we'd add the key, we do left plus equal 1, and then we could just return triplets. Line 17. So we had an extra parenthesis. That's work. Let's see if it works for our overwhelming 0. So it's definitely not the fastest solution, but it's a bit optimized. So 1.4 seconds. I mean, this is not very fast. I mean, if we just think about how this works, right, and the code is all over the place. We even have an array that JavaScript allowed us to declare with no real bearings, right? We're basically doing for every element in the array a algorithm which performs in linear time to check the range, right? In that sense, that would be n times, or maybe this would be actually be n to the n, or for every number in the array, we're going to perform n operations, which I think is n to the n. So I'm thinking maybe the same thing could have been accomplished except with a triple for loop. But you'd still have to sort it. So I want to check that to be certain, but we have 4 minutes left, so let's see if we could do better. Share a similarity that the sum of elements must match the target exactly. Difference is that instead of exactly one answer, we need to find all unique triplets that sum to 0. Before jumping in, let's check the existing solutions and determine the best conceivable runtime for 3-sum. 2-sum uses a hash map to find complement values and therefore achieves O of n time complexity. 2-sum 2 uses the 2-pointer pattern and also has an O of n time complexity for sorted array. We can use this approach for an array if we sort it first, which bumps the time complexity to O n log n. Considering that there's one more dimension in 3-sum, it sounds reasonable to shoot for O of n squared complexity as our best common runtime. So would this be n squared? I mean, for every element, right, we iterate, we can do it, worst case, n operations. So we will follow the same two patterns. Pointer pattern 2-sum 2, it requires the array to be sorted. So we'll do that first, as our best conceivable runtime is O n squared. Sorting the array requires the array to be sorted, so we'll do that first, as our best common runtime is n squared. Sorting the array would not change the overall time complexity. True. To make the result contain unique triplets, we need to skip duplicate values. It is easy to because the repeating values are next to each other in a sorted array. If you're wondering how to solve this problem without sorting the array, go over the no sort approach below. In case when that approach is preferable, in your interview may probe your knowledge there. After sorting the array, we must move our pivot element num sub I, analyze elements to its right. We find all pairs whose sum is equal to negative nums I. So the set sum of the pivot element nums I in the pair negative nums of I is equal to 0. So quick refresher, the pointers are initially set to the first and last element respectively. Compare the sum of these two elements to the target. If it is smaller, we increment the lower pointer. Otherwise, we decrement the higher pointer high. Thus, the sum always moves towards the target, and we prune pairs that would move it further away. Again, this works only if the array is sorted. This is what we were doing, right? It's smaller, then we get here, they pass each other, so we go to the next one. And they go like this, that's possible. Okay, so when they do have a match, they increment both. But it's possible that we could have another -1 here. Implementation is straightforward. We just need to modify 2-sum 2 to produce triplets and skip repeating values. The main function sort the input array. Did that, iterate through the array. If the current value is greater than 0, break from the loop. Remaining values cannot sum to 0. If the current value is greater than 0, break from the loop. Remaining values cannot sum to 0. Oh, I see what they're saying. If the array is sorted and the value is greater than 0, then the remaining values can't get to 0. That's a good observation. The current value is the same as the one before. Skip it, otherwise called 2-sum I for the current position I. So my function set the low pointer low to I plus 1 and the high pointer high to the last index. The low pointer is smaller than high if sum of num sub I plus num sub low plus num sub high is less than 0, increment low, sum is greater than decrement high. Otherwise, we found a triplet, added to the result res, decrement high and low, decrement high, increment low while the next value is the same as before to avoid duplicates in the result. That is a good way to avoid duplicates. And I definitely could have done a 3-sum to abstract out a lot of this right here. That was definitely sloppy. This entire bit right here could be abstracted out to be a function, but maybe not, right, because we're using a set. But it definitely could be broken down to be better. And they skip while low is less than high. So we can still go forward, and num sub low does not equal nums low minus 1. This is O n squared, 2-sum is O n, and we call it n times. It's basically what we're doing. So we iterate over every element in the array and basically call 2sum2. Takes n log n. Overall complexity is n log n plus n squared. This is asymptotically equivalent to n squared. Space complexity from O log n to n to linear time, depending on the implementation of the sorting algorithm. For purpose of the complexity analysis, we ignore the memory required for the output. Since triplets must sum up to the target value, we can try the hash table approach for the 2sum solution. This approach won't work, however, if the sum is not necessarily equal to the target. Move our pivot element nums I and analyze an elements to its right. Find all pairs whose sum is equal to negative num sub I using the 2sum 1-pass approach. The sum of the pivot element num sub I and the pair negative num sub I equal to 0. This is still n squared. So this is interesting. So I'll take that for now, but knowing that there are other ways we could have reduced values or skipped duplicate values besides using a set. So we'll take that for now. And we'll do binary tree level order traversal. Given the root of a binary tree, so we have the root of a binary tree. Our tree looks like 3, 9, 20, 15, 17. And by the looks of it, it sort of looks to be a, no, it's not a BST. Return the level order traversal of its nodes values from left to right level by level. So they want us to return 3, 9, 20, 15, 7. And we do return 3, 9, 20, 15, 7. The caveat being that it looks like the root node should be inserted first by itself, and then we have 2 following, right, which would be the children of that node and the children of the next children, right? So binary order level order traversal. For the example, we have just a tree with a root node. We push on the root node value, and for when the root is empty, right, we return an empty matrix, which is just an array of arrays. So we know that we can have nodes in the range between 0 and 2000, and the values range from 1000 to negative 1000. So I'm thinking the first way we can do this is with breadth first search, which I think by default does a level order traversal. So the version that we could use of this would be BFS iterative with a queue, and then for some of the prerequisites of the problem, we could satisfy those conditions. So the first thing we want to do is say if not root. So if the root is null, right, you want to return an empty array, which is what they do here, right? Additionally, we know that the root, right, starts with a singular. The answer always starts with the root's value as an array. So we can push that on to start. And then our stack, our queue, is going to start empty, and it's going to hold nodes, right, for which we will do a iterative level order traversal. And this is actually going to start with, actually it won't start with this value in it, but what it will start with is while queue.length is not empty, right, we're going to need a cur variable, which is definitely going to start null, and the queue is going to start with root.left as a child and root.right, right? And so cur is going to get the value, right, of queue.shift, which is going to get the value from the front. So we're going to get root.left. So if we look at this as a temporary run right now, we can do a BFS with a level order traversal, with 3 up here, right? 3 is going to exist in the answer, and our queue is going to have left and right, which is 9 and 20. And then while our queue isn't empty, our queue isn't empty because it has 9 and 20 in it, we're going to take 9 off of the queue from the front, and we're going to say not R, but actually maybe R, because we want to store it as an array of the node's values, basically. We can actually take 2 nodes off. So maybe we don't need carp here. So we'll say node 1 and node 2. So we'll take 2 values off, right? And we're just going to say in the case where the value is null, they don't want those values to exist, right? So I think the best that we can do is say if n1, right? Then we want to do r.push n1.val. We can duplicate this line, do it for n2. So we're creating this small array, and then at the end we can do ans.push r, right? But additionally, not only if n1 and n2 exist, right, do we want to push their values on to the array we're using, we also want to push their children on to continue doing a level order iteration. That would require pushing node 1's children if it exists onto the queue. So it's a queue.push n1.left, n1.right. We could duplicate this, do n2.left and n2.right. Then we could push that array on, and we'd continue going until we reach the end. So one quick way to test that this makes sense is that, so we'll just run it very quickly. If the root doesn't exist, we're going to return an empty array. So we're good on example 3. Now our answer, which is supposed to return, the root node always exists in an empty array by itself. That does exist here at root.val, being the first array in the matrix. Then we set up a queue with the left and right children of root 9 and 20. The queue isn't empty, so we pop both of those nodes off. 9 does exist, so we push 9 onto the array, right? We also push its children on, which are both null. So they're both null, so we push those onto the queue, right? And if n2, well, so we push n2's value, which is 20, into this array, push the array onto the answer output. So now we have null, null, and 15, 17. Well, we pull both of those nulls off, right? Check if n1 exists, it doesn't. If n2 exists, it doesn't, right? And finally, right, if, now I'm noticing if answer.length equals 0, or if it does not equal 0, then we would like to push that answer, that array, onto the answer. But since they both don't exist, we don't want to do anything. Then from there, we'll process 15 and 17, which hopefully should give us the correct answer. So we'll try that here. So we're missing some things here. So we're actually getting 3, 9, 20, and we actually have some empty arrays, which is interesting. So let's trace this. Again, we'll have 9 and 20. Once we get to 9, right, if 9 exists, which it does, we push both of its children onto the queue to process, and both of 20's children onto the queue to process. Those do eventually get processed. But in the wake, right, we say if answer.length, oh, not answer, if array.length is not empty, then we'd like to push the array onto the answer. So that works. Let's see if this makes sense. So it's interesting. They're saying 1, 2, 3, 4, and 5. So my algorithm treats a pair of nodes as separate, but theirs treats it as one. So I'm wondering if any time there's two nodes, they should be returned together. So if we try to recreate this array that's giving us an issue, this tree that's giving us this issue, we have 1, 2, 3. So presumably this looks like this. We have 1, 2, 3. 4 null, null, 5. And so it looks like they want 4 and 5 together, despite the fact that they're from two different nodes. So maybe the point is to go for something like whenever we have a pair, we want to push those two on. So we could try for something like that. And so we'll just say if r.length equals 2, then we'll push the answer onto the array, right? And if it doesn't, right, then we'd like to keep working at that. But I don't know if I completely understand this tree and why it's producing this output, but we can try it. We have to so we actually produces 1, 2, 2, 3. Instead of 4, 5. So in this case, let's run through this. We push on 1 by itself into the array. Then we have 2 and 3 as the children to work with, right? Both of them exist, so we push their values 2 into the array and push their children on, right? Which is n1 dot left and n1 dot right, which seem to be 4 and null. And then we know that 4 exists and its children are null and 5, so we also push we also push 3, which has the value of null and 5, right? So right now the upcoming values in the queue would be 4 and null, right, and null and 5. And we say if r.length equals 2, we push 2, 3. But is the queue equals 0? No, so we pull off 2 values. We have null and 4, right? The array equals this IC. So this array would have to be outside of the scope, otherwise it gets redeclared. So we'll do it like this. Whenever we push an answer onto the array, or we want to set it back equal to an empty array to restart the queue, basically, to restart the array. So let's see if this makes sense. Works for this case, but does it work for any of the remaining cases? So when we have a singular node, which is 1, and its children, that's an edge case, right? An imbalanced tree. So they do have me there. And here we can say if r.length does not equal 0, then for certain hands.push array. But I didn't think through a lot of the edge cases, so now I'm kind of solving it by solving the edge cases. So we have 1, 2, I guess I'm unclear as to when nodes should be grouped together in the array and when they shouldn't be. In this case, it looks like nodes are typically grouped together when they have the same parent node, but in an example we saw earlier, it wasn't the case. So we have 1, 2 null, right? So if we look at the 2 children, it has 2 and null, right? And so 2 and 3 do not have the same root node. In fact, 3 is a child of 2, yet it's being given a singular value in the array. So I'm kind of thinking this part where I was doing this, if the array length equals 2, doesn't exactly make sense long term. I'm thinking maybe we just want to push the answer as is. And so I'm pretty sure we'll rerun to a originally we did have if r.length equals 0, then we for certain do not want to add any values to the answer. Not that it equals 0, but it does not equal 0. So seems to be something we're misunderstanding in exactly what mechanism or why 2 nodes should be fused. So in this one, which is what we had earlier, we have 1, 2, 3, 4 null, and null 5. Why are 4 and 5 being fused? They don't share the same parent, but they're being treated as a pair. Return the level order traversal of its nodes values, i.e. from left to right, level by level. So it's interesting. Somehow this is producing it's unclear into what exactly or when 2 nodes should be fused. If we do the level order traversal, we would visit this like 1, 2, 1, 2, 3, 4, 5. But as we view this in the future, we run into different problems where we have a tree that is broken up completely. So maybe when a node is not a direct descendant of a node, it should be given its own singular value. If that's the case, that might demystify the root node. For some reason, the root node shares the same potential format as these singular nodes. Now, I presume this tree might look something like this. It should be 3 and null, right? Then we would have 4 and null, and then we would have 5. So in some case, there's something here that makes or forces this node to be treated or forces these nodes to be treated like independent portions. And I'll delete this right-hand side because in this case it doesn't exist. 1, 2, n. So maybe when its buddy does not exist, it should get. So maybe if the current node, right, didn't have a brother or sister, maybe it should be considered a singular node. So one way we could check that is if we do if n1 and n2, then what we can do is just do answer.push n1.val and 2.val. We can now delete this one. We don't have to worry about pushing anything onto an array. And what we could do is say, otherwise, if n1 or n2, right, then one of these values doesn't exist, right? And we can decide that by saying if n1 exists, right, and set this value equal to n1, otherwise set it to n2. And then we'll say, instead of pushing these values individually, we have to push them into an array. We'll do answer.push a singular value of exists.val by itself, and we can remove these array issues. So if a node doesn't have a buddy, then it should be put by itself. So here, oops, I said ans.push. We want to push exists.val as an array by itself. And this should be else if as my. So else if, right, we would do this one, but we still have to push the children on, so we could still do, and this is actually my mistake, we still have to push the children on regardless. This would be q.push n1 dot left or n1 dot right. We do n2 dot left and n2 dot right. Right, and we don't know if they exist, so in one of these cases, so we might just have to, in case of n1 and n2, we want to push both of their children on. In the case of this, right, we only want to push the children of the one that exists on. And we can do this with exists. And we should be good there. And so we're still not getting the correct answer. 1, 2, 3, right, with 4 null and null 5, but 5 doesn't have a buddy, and in this case 4 and 5 are still together. So I feel I'm still a bit struggling to understand when nodes should be grouped together, when they shouldn't. At this point, I feel like I can do the binary tree level order traversal, but at the same time, it's hard to decipher exactly why. It's hard to decipher exactly why a node should be grouped with another node. We tried grouping based on siblings, but maybe I think I see what I'm saying. I think I see what's happening now. Is it guaranteed that all of the lengths of these arrays should always be 2? Or is it that, even if I check my submission, I think these arrays are generally smaller. I think what each array represents is actually the level of the tree. And 4 and 5 are included in the same array because they're part of the same level. Interesting. If that's the case, that does change things a little bit. We do 3, right? And we do 9. We'll iterate through 9. We'll get 3, right? We push 9 and 20 onto the queue. We go to the next iteration. We'll pull 9 and 20 off, right? And we're going to want to visit all their children together. We push 9 and 20 on together. Now in the larger case, if 9 has children, right? The array, if 9 has children, on the next iteration, right, we would pull off null, and we'd pull off let's just say 5 and 6 if those values existed. We would say they both exist, so push them onto the array. Then we go to the next iteration, pull off 20, and do the same thing. So we need a way to merge these by level, and I'm thinking each iteration pushes a level onto the stack. So it could be that the way to get all the levels done for a particular stack. So if we have 3, right, for a particular queue, if we have 3, we're going to process all the nodes here. It's only going to be 2, right, 9 and 20. And if this is the case, you could do 9 and 20. So let's just say we did another inner while loop while the queue.length does not equal 0. Right, we'd have 9 and 10. We'd take them off the stack. Off the queue. We would take them off the queue. Push all their values into an array. Push that array onto the answer. And then push their children onto the queue afterwards. So I'm thinking this whole thing, so we're thinking array by level order. Let's get this all out of the way. So if we have root.left and root.right to start, that's 9 and 20, right? You want to say while queue.length does not equal 0. We want to process these nodes. And to do that, what we want to do is say, we want to say R while queue.length does not equal 0, right? What we want to do is say I'm kind of thinking of an inner and outer queue scenario. It might be simpler if we use the same queue. We'll say while queue does not equal 0. So we have 9 and 20. Right, we want to push naively onto the array so we'll push that node, right? We'll get that node's value off, right? And we'll push it. We'll say r.push node.val. So we'll push that value onto the array, right? And then we'll keep going, right? We'll do 9, we'll do 20. Right, but we still want to process those nodes as children. So once we get to queue.length equals 0, right, we want to do is say ands.push the array, right? What we'll have is a processed, right, which will allow us to, right, after we process the node, right, we push it onto process so we can take their children, right, and push it onto the inner queue. We can push it onto the queue to be processed. Say processed dot push node dot left node.write. This will allow us to process all nodes in a level, right? And then once we push the array, what we'll do is we'll pretty much just push q.push. What we can do is just say q equals q.concat processed, and this should keep going over and over again. So a quick test, we push the empty array of 3 onto the array. It's the only one on its level. We have left and right in the queue. The queue isn't empty, so we go in. The queue still isn't empty because 9 and 20 is in it. We pop 9 off of the queue. We take it from the front. We push the node's value onto the array, which would be 9, right? And we push its 2 children, which are null, onto the queue. Right, so we still have to figure out or handle it when the node doesn't actually exist, right? That being said, we have null and null now unprocessed. Then we go to the next node, which is 20. We push 20 onto the array, and we push its children, 15 and 17. From there, the queue is empty. We push the array of 9, 20 on. Then we can process. We concatenate the process array with the original queue. The queue isn't empty because we have null, null, 15, 17. Right? We go in, the queue isn't empty. And this is the entire level, so we're going to process it. But we want to ignore if the node's value doesn't actually exist. All right, so we want to ignore those values. I think we should be able to do something here. So we're actually looking good in terms of output. We have an extra array. We're saying q.concat right, and we want to make sure the array actually exists, right? So we can just say if r.length is not equal to 0, right? Then you actually want to push something on. And so I think the question quite literally meant the level order traversal of its nodes. So if we run this, I'm feeling pretty confident about this one. Nice. So yeah, I think that's why clarifying questions are really important. That is interesting. So I read the problem and immediately assumed that it should be two node children. What they're really aiming for is a level. Each array represents a level in the binary tree. That's pretty cool. Let's see how they did it here. I mean, the time complexity of this would be linear time because we're just visiting all the nodes in the tree, with space taking linear time where linear space where n is the number of nodes in the binary tree, where this space would be taken on the call stack because recursion tends to take up space. There are 2 general strategies to traverse a tree. Depth first search. In this strategy, we adopt depth as a priority. So that one would start from a root, we draw it down to a certain length and back up to a root to reach another branch. The DFS strategy can be further distinguished by pre-order, in-order, and post-order, depending on the relative order among the root node, left node, and right node. Breadth first search, we can scan through the tree level by level, following the order of the height from top to bottom. That's what we did. Nodes on the higher level would be visited before the nodes with lower levels. On the following figure, the nodes are enumerated in the order you visit them. 1, 2, 3, 4, 5. That's obviously the version we did was actually iterative. So iteration, the recursion block will be written in iteration form. Let's keep nodes of each tree level in the queue structure, which typically orders elements in a FIFO manner. In Java, one can use linked list implementation of the queue interface. The queue structure will be overkill since it's designed for a safe exchange between multiple threads and hence requires locking, which leads to performance loss. In Python, the queue implementation with a fast, atomic, append, and pop left is dec, The 0 level contains only one new row. The algorithm is simple. Initiate a queue with a root. Start from the level number 0 level equals 0. While queue is not empty, start the current level by adding an empty list into output structure levels. Compute how many elements should be on the current level. It's a queue length. Pop out all these elements from the queue and add them to the current level. Push their child nodes into the queue for the next level. Go to the next level. So they start with the queue and they add the root. Level equals 0, so levels.add, which is going to be a list of numbers, which is what we return. They just add new array list with an integer and the number of elements in the current level. So level length equals q.size. So I equals 0 up to level length is one element because it's root. You remove the node. Then we do levels.get. Levels.get level. So for the current level, we add a node value to it. Otherwise, we add child nodes at the current level in the queue for the next level. So if node.left does not equal null, then we add the node left. Otherwise, we add the node right. Go to next level. That's an interesting implementation. Interesting. So I would say that is acceptable for now. We have 22 minutes left, so let's try for clone graph. So we have clone graph, which is a node. A node has a value. And we have neighbors, which is an array of nodes. Okay. So a node has a bunch of neighbors, and each node can have more neighbors, so it's a graph. But it looks like an adjacency list representation of a graph. So given a reference of a node in a connected meaning they're all connected to each other, undirected graph, return a deep copy or clone of the graph. That's an interesting issue. It's kind of like, reminds me of finding a cycle in a linked list. Each node in the graph contains a value int and a list node, a list of its neighbors. Test case format. For simplicity, each node's value is the same as the node's index. One index. For example, the first node with value equals 1, second node with value equals 2, and so on. The graph is represented in the test case using an adjacency list. An adjacency list is a collection of unordered lists used to represent a finite graph. Each list describes a set of neighbors of the node in the graph. The given node will always be the first node with value equals 1. You must return the copy of the given node as a reference to the cloned graph. Example, original graph is 1, 2, 3, 4, and we can see they're connected. This looks like a clone. The nodes are new. Graph looks the same. You can't return the same graph. The nodes were cloned, but the graph is messed up, doesn't have same connections. I see what they're saying. Don't return the same graph and keep the connections the same. So the adjacency list is 2, 4, 1, 3, 2, 4, 1, 3. So what that looks like is for 2, for index 0, wait. So how does this, so you know a node has a node value and an array of neighbors. There are 4 nodes in the graph. First node, val equal 1, neighbors are second node. I see, so 1, 2, 3, 4. 3 is connected to 2, 4. 4 is connected to 1, 3, and 1, 3. And 2 is connected to 1, 3, and 1 indexed array 2, 4. 1 is connected to 2 and 4. So we can see that with an empty graph, we should return it nothing. Oh, no, this is not empty. It's just a singular node that has no connections. Graphs consist of only one node with value because one does not have any neighbors. Interesting. So we still want to copy. We have to make sure that we know the existence of an array means the node does exist. Adjacency list is an array. This is an empty graph because there's no arrays. I guess the way it's output looks like there's no arrays, but there's no neighbors in the array. Number of nodes in the graph is in the range 0 to 100, and the value for each node goes from 1 to 100. And the val is unique for each node. There are no repeated edges, no self loops in the graph. Graph is connected and all nodes can be visited starting from the given node. Interesting. So cloning a graph, my first instinct is to use something like we would do for detecting a cycle in a linked list. We could have a node, right, which is going to visit every node in the graph, but in a sequential fashion. So 1 might go to 2, might go to 3, but we'll also have another node which is following behind that node, but it's behind. And if they're ever equal to each other, then we'll know that we've copied the whole list, basically. My only worry with this algorithm is that we're doing work until they meet each other. So if we're doing work until they meet each other, it's highly possible. It's highly possible. It's highly possible that they could do extra work. So if that's the case, maybe this might not work. So naive approach, linked list cycle, 2 pointers. Could we brute force this? I think you need a way to check whether or not you've seen a node before. So I think in some way, I think the key to the problem lies in being able to tell when we visited a node before. So we're going to do a deep copy. One way we could do that if every node is unique, maybe we could try to visit every node, right? And we'll have a set, or I guess a map, right, which maps to the particular node's value and to the adjacency list that it's connected to. Right. And if that is the case, or the nodes that it should be connected to, if that is the case, then we should be able to wire this all together, since for a particular node, you could iterate through the map. So for a particular, so I think if we have a map basically of node, and when I say node, I mean node index, to the values it should be connected to. So it should be 1, right, connects to 2, 4, right? Then I think we should be able to do this to create this map. Could create this map with recursion and a map which we share. But additionally, it's also possible, if we do this with recursion, we can do 1 to 2. And once we create the map, how could we go about creating the deep clone? Well, it seems like we could just iterate through the map and then for each index, we'll add 1 to it, and we could just connect it to its neighbors. 1 to index and connect to neighbors. But we do have to return a node. So let's try this approach. If we can create this map with recursion, let's try that. So we'll call it create map, which would be a function, and create a map, right, which would be a new map, which maps a number to a node, or we could just call it traverse, and it'll take the map, right, but it will also take the current node, which can be node or null, and the map will get the same type that we already have, and it doesn't have to return anything because it's going to be modifying the map by reference. And so we basically call traverse with the root node and the map. So if we're going to do this, maybe there's a few different ways we could do it. Since we're using a recursion, we want to visit all the neighbors, right? And so how do we know? So the node, each node's value is the same as the node's index. For example, the first node with value equals 1, second node with value equals 2. So addition, I think they did say that there are no connected, or there's no repeated edges and no self loops. Oh, since there's no repeated edges and no self loops, we can just do maybe a depth first search, and we can use the value as the ID. So say if map.has, so first we're going to check if the node exists. If the node exists, and the map has a value for the node, the map has seen this node's value, which is essentially its ID. It's seen this node before. So let's just say earlier, if we look at this, we look at node 1, we visit 2, right? Since we're visiting 2, right, we've already been, we're visiting node 2, so this would be here, right? Now we're going to visit node 1. We've already been to 1, so we're going to skip it. Now we're going to visit node 3. As visiting node 3, or we're going to visit node 3 and get its neighbors. And if we've seen a node's value before, we basically want to ignore it. And so I think one way to do this, we could actually do it like this. So if we create an array, right, with the node itself and the nodes node.neighbors, and we could do a for each, and we'll do what is in here. So with the first node, we're going to pass in node 1 basically, and we're going to visit 1, right? Actually, we don't actually have to visit. Do we have to? We're already at the node, so we don't actually have to visit the node itself. So maybe we can just do node.neighbors. We do have to do something with that node's value. And so our map is to create a map of the node index. So here we'll say if the node exists and the map has not seen this node's value, which is essentially its ID before, we want to add it to the map. say map.set node.val equal to its neighbors. Let's set node.val and to its neighbors. When we iterate and add 1 to index and connect to, what we want at the end of the day is the potential to be able to iterate over the map. It's indices. So we said iterate through the map, but if we have a map of node values, which would be 1, 2, 3, 4, to their neighbors, how would we connect them? Could create new nodes at its value equal to this, then create nodes 2 and 4, which we also connect values to. Then we could continually iterate through setting those values. So rethinking this approach, even if we produce this map, let's just say we produce the map of the node's value to its neighbors. The goal of that would be, because iterating over a map is simpler than searching through the graph to copy it. So let's just say we created something like this. Have 1, 2, 3, 4. Where 1 is connected to 2 and 4, 2 is connected to 1, 3, to 2 and 4, and this is connected to 1 and 3. So how could we go about creating a graph from this? We iterated through the map while also keeping track of the keys. We could create a new node with the value set to 1, and then we could create 2 more nodes. So I think what we could do is we'd have a second map, which would be the new nodes that we're creating. So create a new node of value 1, and we'd set it to the, so basically you just have to copy the map. So we create a new node 1, set it to the map, and then if 2 and 4 we've never seen before, we'll create nodes for them and set them equal to that. No, we can't. So if we have 1, we basically have to go through and create a node for each of the keys, which would be 1, 2, 3, 4, and then create a map of value to nodes. And then you could actually iterate over the map again in a 2-pass, and then add those nodes into that node's values, basically. And then we could return basically map or copy.get node.val, which would be the start. So if we can assemble this tree of right, and it's in node form, so really we just want to get it to map form. So we'd set the node.val, right, and we want to set the value, we want just the values of the neighbors. And it would be 1 index, so we'd say neighbors dot map node.val. And so we have neighbor vals. which ends up working. And then for each of the neighbors, we'd like to do the same thing. We also right, so earlier we excluded node. I think we can exclude node. I think we can include it. And copy these two lines into here. We'll say if the node exists and the node does not have a value in the map, then we want to set it to node.val and to neighbor vals. So let's see what we get from map. We'll just return all for now to double check. We should have commented this out. Argument of type number. No, and right, we said our was going to be map to a node. Now we know it's just going to be a map to an array of numbers, so we can change that. So you get 1, which is connected to 4, 2, which is connected to 1, 3, and 4, which is connected to 1, 3. Node and the node's neighbors. So we're missing 3 here. So you have 1 arrow, 2 arrow, and 4 arrow. We're missing. So I'm assuming we go 2. Right, then we go from 1 to 2. From 1 to 1, but we've already seen this node. So we should go to 3. And then we should map.set to node.val. So we should just be able to check. So we say node, we're passing in this node to start, which is 2, 4, right, which is node 1. We check if the node itself, which is 1, right, I think we actually have a shadowing problem. For each cur, and it should be cur.neighbors, and n will just be n. Map.set cur.val equal to neighbor. So you still get 1, 2, 4. If the map with the node neighbors, and for each turns to cur. If cur exists and the map doesn't have a value for cur.val, then we do cur.neighbors.map n to n.val. We set map.set cur.val. So we go into this one with node 1, which means we're going into index node 1 twice. Could be including node twice. So we actually don't visit. Oh, they're not. It's not completely connected. There's no loops. So if we do node, and this is actually not recursive. So if we set cur.neighbors equal to map n.val, we already set up those values. We'd also like to traverse cur and pass in map. So now we actually have it matching up because we forgot to actually traverse. Now we have the map that we're looking for. So now that we have the map, and I was unclear with my instructions here, we should create a map of 1 to the nodes. So now that we have the map, how could we construct a copy? So I think so for each val and neighbors of map, we want to do a copy, which is going to be a new map of number, not number, but of number to nodes. We'll say map.set val equal to new node val. This will be the map copy. Now that we have this, we can iterate through the original map again and just set up those connections. So say neighbors, right, equals an array. We want to set so we're iterating through the map that we've created. We have the value in the neighbors. So we'll say neighbor copy. So these are just the neighbors. So we actually don't need the neighbors that when we're iterating through, we just need to access the value. But in this version, we actually do need the neighbors. Now we want to copy or create those connections. To do that, we would say map copy get the value of val, but set its neighbors equal to neighbor copy. And here we can do for const n of neighbors. All right, we can just say neighbor node. So this n is just a number in the map, but to actually get the neighbor node right in this copy, we actually have to do map copy dot get n dot val. We can just shorten that to neighbor copy dot push at copy dot get n dot val. Then map copy dot get val dot neighbors equals neighbor copy. And then to return the first node, we can just get map copy dot get the original node we started with, which would give us the start. Cannot find a neighbor copy. Neighbor copy. Then we would now have the references. So let's see if this works. Value is not iterable. This is in line 56 in Traverse. Intermediate value is not iteratable. So you would do something like this. Equal, right? If node exists, right, then you actually get an array with the node value. Otherwise, you get an empty array. Then we can do another one. We'll say if node dot neighbors, right, values dot push node dot neighbors. And here we can just do values dot for each. Turn map dot copy get val. Null reading val. So val should exist unless the node they're giving us is null. We forgot to code that part out. So if not null, and if not node, then return null.